Okay, we'll do a quick review of some of the trig you need. So SOHCAHTOA, this is the primary trig ratios in the red box on the top. That's all you need. So that's sine, cosine, and tan. Remember, they work with 90-degree triangles only. If you happen to know sine law and cosine law, you're welcome to try and integrate them where you want, but I will only be using SOHCAHTOA to solve the problems. We'll be doing a component approach that will focus on that. So we'll be doing primary trig ratios only. That's all you need. So quick recap, find the missing sides and angles for the following triangle. So if we look here, we have a 90-degree triangle outlined by this box right here. We're given 22.6. The sum of the interior angles of a triangle have to be 180. So pretty quickly we can find this is 67.4 degrees. Okay, if we want to find the missing sides, let's go after B. So I'm going to use the given 22.6 and B, which would be adjacent to that angle. So if I went cosine of 22.6, that is the adjacent over the hypotenuse. This value of cosine 22.6, that's just a number. You can always just punch it in your calculator, or you can look it up on a table if you want to go old school, and it would become 0.92. There's a few more decimals, but we'll round it off there. So now if we times that by 13, we get 12 is our value of B. Okay, so this is 12. If we want to go after A, this is the opposite to this 22.6. So we could use sine of 22.6 equals A over 13. And if you do the same thing, sine of 22.6 equals times that by 13, you should get 5 as your A value. Okay, that's a quick recap. So reminder, this angle is where I'm starting, this is adjacent, this is opposite. If this 67.4 is the angle I'm working with, then this turns into opposite, this turns into adjacent. The hypotenuse never changes location, it's always across from the 90-degree angle. Okay, that's all you really need. Okay, so our goal today, by the end of today, I'll be able to calculate the displacement of an object in 2 dimensions using an algebraic technique that we're going to call components. So we have a couple different ways of adding vectors. We'll highlight them. This is a bigger topic for a future math course. So we have the triangle law for adding 2 vectors. So you'll notice again, we have little vector A plus little vector B gives me the resultant red vector. So we create a triangle, and we have to remember we're placing the adding vectors tip to tail. We could also use that same mentality to create a parallelogram, and both of these shapes have other geometric properties we can take advantage of. Triangles have the sum of the interior angles is 180. Parallelograms have the transferability of knowing where certain angles are in parallel lines. So going way back to grade 9 math. So that's why we would draw those, because we can transfer information a little easier. And we have another cool feature of vectors is that you can move them around. Okay, so when you have these 2 vectors A and B, if they were drawn like they're shown with dark here, you can actually take this vector right here and you can pick it up and move it around. And that's what these little dashed vectors are at the top. So if you're looking at this purple set of vectors down here, there's nothing that says we can't take these, clone them, and just move it up and make a parallelogram. Just like that. And the resultant would still be going from here to here. Okay, and it makes it easier to see. Okay, so that's just a bit of vector overview. If we add 2 vectors together, you'll notice I have A and B here. So if I move these around, here's A plus B. We could start with that kind of a picture. This black dotted one here is a, let's move it all down, is a copy of B, so I could place them tip to tail. Move this guy over as well, and I've created both my parallelogram and my triangle. This green one is the resultant. Okay, so that is the resultant of A plus B. You can write the B on the top or the bottom. It doesn't matter. Okay, so we could use either parallelogram or triangle. Now when we get to three vectors, here's three vectors, A, B, and C. Okay, parallelograms and triangles go out the door, and we end up with just this long vector here. That's my resultant. So this is my resultant. Okay, and so there is a technique which will allow us to solve this problem, and it won't require using either the triangle or the parallelogram technique. It's called components. Okay, and so what we're going to do is we're going to chop a whole bunch of things up here. And I'll show you how to do that in a second. All vectors can be written as a combination of other vectors. That's a really important idea. We usually use component vectors in the x and y directions to describe a vector. We do this because we're familiar with it. Okay, we like ups and downs, lefts and rights. It's generally easy for our brain to tolerate. So if I have this vector right here, z, it's 40 meters at east, 20 degrees north. So let's do a quick check. East, this is east right here, turn 20 degrees to the north. So this angle in here is 20 degrees. So I want to know which pieces or what are the x and y components of that. So we can take our primary trig ratios. If I take cosine of 20, that is going to equal x over 40. And if I punch that in my trusty little calculator, I get 37.6 equals x. Okay, if I solve for the y component, I could use sine of 20 equals y over 40. And sine of 20 times 40 is 13.7. Okay, so what we could say here, and this gets a little bit beyond where we want to go, but z is equal to x vector plus the y vector. So z is equal to 37.6 east plus 13.7 north. Okay, so we've taken that 40 meters and we've broken it down into its x and y pieces. Okay? So find the resultant of adding AB and BC together. So we're going to do one with a vector scale diagram, and I have it already laid out, so I'm not going to spend the time drawing that. If you want to pause it and refresh your vector scale diagram skills right now, that would be an awesome idea. So we'll call this method 1. We'll draw the two displacements using a ruler and protractor. We'll draw the resultant vector, and then we'll measure the sides and angles of AC, which is our resultant, to see what we get. So we have 10 kilometers at east, 20 degrees to the north, so we're heading in some direction like that, followed by 12 kilometers at, now this is just a bearing at 15 degrees, so if you remember, we start at north, we turn 15 degrees, and then we travel this way. Okay, so those are two sketches just of what my vectors are going to look like to make sure you have the right directions. If we draw them here, there are my two vectors. So east 20 degrees to the north and just a bearing of 15 degrees. So my resultant, okay, my resultant, I'll take that in a minute. Let's bring our ruler over first. If I bring my ruler in here and I measure from A to the end of C, okay, I am measuring almost 10 centimeters. Okay, so we just have to go back over what our scale is. So if I take this and let's say, I'll check our scale. Come on. Okay, it looks like each centimeter is worth 2 kilometers. So 1 centimeter equals 2 kilometers. I just should have written that down earlier. But you can see from A to B, that's a 10 kilometer measurement, and I have 5 centimeters on my ruler. So my 10 centimeter resultant should turn into a 20-kilometer solution. Okay, and now if I bring that in, we can see there's the 20 kilometers. Okay, and now the 40 as my direction. If I put my protractor on there, I can see I have 50 degrees up to here, so that means I have 40 degrees from north, so I'm going north 40 degrees to the east, or I can just say at 40 degrees. So there's using my vector scale diagrams to come up with the answer. Now we're going to do it with the algebra. So we're going to take all of our two-dimensional vectors and break them down into their horizontal and vertical components. We're going to do all of that with primary trig ratios. We're going to sum up the x parts, and we're going to sum up the y parts, and we're going to find out that will give me the components of the resultant. Positive and negative directions are super important. Okay, so now I have a link here. Let's hope it works. And of course it puts it on the other screen. And it will link us to a PhET simulation. Maybe we could minimize it, get it all to fit. All right, so we want to look at Explore 2D. So if we click on that, hopefully it's inside. You can drag a vector onto the screen. Okay, so there's A, and you'll notice it gives you all of the components that make up A. So it has the magnitude, it has the angle it's measured at, and it has both the x and y pieces. If I drag a second vector B on here, and I highlight it, and I drag it, it gives me all of the properties of B. If I drag C on here, and I make C go from beginning to end, okay, so C would be my resultant. I can turn on some of the pieces of information, and you can see, no pun intended, that this component here, okay, of the A vector and the x component of the B vector, they combined to make the x component of the C vector. And you could do the exact same thing with the verticals. Okay, that's the y component of the A vector. This is the y component of the B vector. If you add those both together, you get the y component of the C vector. Okay, and that is not a fluke. That is one of the cool properties of working with vectors in 2-space, is that you can break them down into any x and y components, smash them all together. You could do this in a spreadsheet, you could do this a whole bunch of different ways, and it will always work out to create one large triangle, and the large triangle is right here. Okay, so you can do this with 2 vectors, 3 vectors. In fact, I'd strongly encourage you to try exploring this software. It's pretty powerful. Let's go here. It's got all my old vectors on there. Let's get rid of them. So this one we could have more than one vector. There's a V. I'll tearing that one down. I'll take this guy and move him down. So there's 3 vectors added in a row. We put this one at the start, and we drag to here, and you can see the parts. Okay, and they all add up. Now what's important to note on this one, this is a positive y direction. The second vector has no y direction. The third vector has a negative y direction, and that's really important. So this one here is positive, this one is negative. They'll cancel out, and their sum, or their result, in that component direction will just be that small amount. Okay, that's the big idea. I would encourage you to explore that a bit more. So let's get started. I find a certain setup makes this a much easier problem. So we're going to take AB, which is 10 kilometers at east 20 north. That's this bottom triangle, and I'm just going to draw it and then drag it out of there. That's the triangle I'm looking at. So I'm going to drag that out. This is 20 degrees. This is 90. This is 10 kilometers. This is x. And this is y. So if we go through and we do a quick solve, cosine of 20 is x over 10. And I won't do all of these on the board just because it's a little bit time consuming. Cos 20 equals times 10. We get 9.4. Okay, and then if we do the same thing with sine 20 equals y over 10. So sine 20 equals times 10, 3.4. Okay, and then what we would do is we'd have to put these into our table. Now we don't want to just willy-nilly throw numbers in there. We want to have a consistent system. So our positive directions are generally up and to the right. You are completely allowed to change those, but this is what I'm going to use for this question. So we have 9.4 as my x component of the 10 kilometers, and we have 3.4 as the y component. Okay, if we go to the next triangle. Okay, so I'm just going to draw that triangle, and then I'll drag it down. Oops, I'll drag it down so I can see it a little clearer. Okay, so now I need to fill in a few pieces. The 15 degrees is outside the triangle. I could have drawn it a different way. So this would be 75 degrees inside. This is 12 kilometers here. This is my y, this is my x. Okay, so let's go cos 75 is x over 12. I got 3.1. Okay, and then again, I'm looking at this as going this direction from here to here, so those are both positive directions. I should have highlighted that on the previous vector or previous drawing. These are going to the right and up. This is going to the right and up, so those are all positive directions. So I would get 3.1 here. And now if we do sine 75 is y, oops, running out of space, my apologies. Sine over 12, I get 11.6 is y. And again, all of these directions are going in the positive direction. If I had something going against the positive direction, I would have to put a negative sign in. If we add these up, we get 12.5 and 14, 15. Okay, so now that vector right there, if I went 12.5 up, sorry, 12.5 to the right and 15 up, I would create this really large red triangle. So this is 12.5, this is 15, and you'll notice you've made a very large right triangle, which we can now use both Pythagorean theorem and SOHCAHTOA on, which are skills we have in abundance. So if I come down here and I say my displacement is 12.5 squared plus 15 squared, this is just Pythagorean theorem. Come on, there we go. So 12.5 squared plus 15 squared equals second function square root answer. I get 19.5 kilometers. Okay, and now because I have that triangle where this is 15 up, 12.5, if I want to find that angle inside there, I can do tan theta equals 12.5 over 15. And I get 39.8 degrees. So if we take those values right here, that is our resultant. 19.5 kilometers at 39.8 degrees. If we jump back here and we look at what those values were from our diagram, that's pretty darn close. Okay, so we had 19.5, I think. We drew 20. We measured 39.8 or something. We measured 40. Okay, the value of the vector scale diagram cannot be understated. It can get you an answer where the calculations take a lot longer. Okay, so the key for you to walk away with is this table is the key piece to organizing your information and making sure you have your proper positive and negative directions written on the page. If we were going to do 3 vectors, I just modeled this with the PhET stuff, but you can see here are the parts as well. Here's the positive x, positive x, positive x. All 3 of those pieces go into making that large resultant triangle on the bottom. Okay, and then you'll notice how the positive y's and the negative y's cancel each other out right here and here. Okay, they don't fully cancel, but they leave us with a small difference. Okay, so the directions are important. This is a summary from your textbook. Okay, it's in the last page or last section of 2.2. So if you want to have a little summary. And then I'll leave you with these two. So if you want to pause this and try it, I'm not going to go through them all right now. Maybe I'll do them in a separate video. So pause it, give them a whirl. Okay, so if you've had a chance to draw or come up with these, here are the answers. Should be about 4.94 centimeters, east 76 degrees south, and 2.62 meters west 49 degrees south. Okay, so this will take a little bit of practice to get our heads wrapped around, but we'll do it. Okay, so we'll finish off with page 75. 1, 4, 5, 6. The more you practice, the easier this gets. Neatness makes a huge difference, and really good bookkeeping is important. Thanks for tuning in.